Hi everyone, I'm Kiyanoush Nazari, and I'll be presenting our paper titled Deep Functional Predictive Control, Robot Pushing 3D Cluster Using Tactile Prediction. Pushing flexible objects in a cluster in 3D is a challenging physical robot interaction task, and the complexity is because there is no dynamic model of the interaction, there is large degrees of freedom of the environment and the task, and there is high stochasticity of the robot action results. Pushing a strawberry stem in cluster is an example of such tasks where the flexible stems, leaves, and unripe fruits make the pushing action very challenging. Model-based approaches usually try to model the environment with pre-existing knowledge, such as grasping an object with known size and stiffness, or manipulating a cable where the precise position of the cable is known. While for more complicated scenarios, such as strawberry pushing in cluster, we do not have this pre-existing knowledge. And in this task, modeling the unstructured environment with high degrees of freedom is not feasible. We can use tactile feedback in these cases to learn the interaction dynamics and use it for control. For instance, in the case of pushing a strawberry stem, the objective is to execute a pushing action while keeping the stem location constant on the tactile sensor and avoid having a slippage, which leads to task failure. Our proposed approach is called Deep Functional Predictive Control. This approach consists of three main blocks, namely Deep Tactile Forward Model, Deep Contact Localization Model, and Deep Functional Predictive Control, which aims to use real-time predictions of the first two blocks to minimize the stem displacement on the tactile sensor within a prediction horizon. The tactile forward model is an action condition recurrent model which uses a history of tactile states and robot actions to predict future tactile frames. And the contact localization model maps those predicted frames from the previous block to a stem location on the sensor. These predictions are used by the deep functional predictive control to minimize the stem displacement. Here we see an example of open loop execution of a pushing action. We see that the stem slippage can cause the task failure where the stem goes off the tactile sensor. In this case, we see a closed loop example where DFPC generates some robot wrist rotation to counteract a slippage, which leads to task success. We test the DFPC for different initial contact zone on the sensor, namely zone 1, zone 2, and 3, and show its effectiveness for all zones. And also, we test two different pushing trajectories, namely linear push and circular push, and test the controller in both cases. We compared the performance of the DFPC with a PD controller. For a linear push, we can see that while the DFPC keeps the stem location constant on the sensor, the PD controller leads to having some displacement, although it leads to task success as well. We do the comparison for a circular push scenario as well, and we see that the DFPC again leads to a smaller displacement of the stem. We test the controller and do the comparison for pushing a stem in a cluster as well, where the target stem is the first one which comes into contact with the sensor. And we see the outperformance of the DFPC with respect to PD in this scenario as well. And we'll have the same comparison for the case of circular push for a cluster of strawberries too. Our quantitative results shows that DFPC outperforms the PD controller with different metrics such as the stem maximum displacement or number of slip instances. So DFPC does not need an analytical model of the interaction for doing control, but it needs a data set to train the tactile prediction and the localization models beforehand. Thank you.